dazzling aesthetic of the Atchison, Topeka, and Santa Fe Railway's iconic Warbonnet paint scheme has spent decades masking a ruthless, calculated, and highly standardized industrial weapon. To the traveling public of the post-war era, the gleaming stainless steel flanks and vibrant red and yellow nose of the Electromotive Division F7 diesel locomotive represented pure mid-century optimism. It was a streamlined arrow pointing directly toward a glamorous future, promising high-speed luxury across the desolate expanses of the American Southwest. But beneath that meticulously styled exterior, designed by artist Leland Knickerbocker to evoke indigenous Native American motifs and sell premium passenger tickets, beat the heart of a mass-produced corporate assassin. This machine was not built for romance, nor was it constructed to preserve the bespoke craftsmanship that had defined railway engineering for over a century. The EMD F7 was engineered with a singular, unromantic objective, which was to systematically dismantle and replace the entire infrastructure of steam power through modular efficiency, standardized parts, and brutal economic arithmetic. To understand why this specific locomotive became the definitive turning point in American motive power, one must look at the desperate financial crisis facing railroads in the years immediately following the Second World War. During the conflict, the railroads had run their massive steam fleets into the ground, moving unprecedented amounts of wartime freight and personnel under grueling conditions. Massive steam locomotives, like the Santa Fe's towering 3,700 series Northerns or their heavily armed 210-2s, were magnificent feats of mechanical engineering, but they were also financial black holes. Steam power required a sprawling, incredibly expensive logistical tale consisting of massive coal chutes, oil bunkers, ash pits, water towers, and roundhouses staffed by armies of highly specialized boilermakers and pipe fitters. A steam locomotive fundamentally consumed itself as it worked, tearing apart its firebox stays and wearing down its massive forged side rods with every revolution of its driving wheels. The railways were bleeding capital on maintenance, and they desperately needed a machine that could stay out on the main line for days at a time, generating revenue rather than sitting over an ash pit being rebuilt by hand. The Electromotive Division of General Motors offered a solution that promised to eliminate the bespoke blacksmithing of the steam era in favor of automotive-style assembly line production. The F7, introduced at the end of the 1940s, was the culmination of over a decade of iterative engineering, refining the flawed promises of earlier diesel models. Earlier iterations, like the infamous F3, had proven the concept of the diesel-electric freight locomotive, but they were plagued by teething troubles, particularly regarding water leaks, fragile traction motor insulation, and electrical fires. The F7 was not a revolutionary leap forward in horsepower. Rather, it was a desperate stabilization of technology, a machine where the engineers finally solved the catastrophic reliability issues that had kept old steam men laughing at the new technology. The Santa Fe adopted the F7 aggressively, wrapping the passenger variants in the glorious Warbonnet colors to haul the Super Chief, while ordering vast fleets of freight variants in the more utilitarian blue and yellow scheme. If detailed technical breakdowns of historic locomotives and railway engineering interest you, subscribe. I have got more of these coming. The core of this mechanical triumph, and the true reason the F7 finally conquered the stubborn railway industry, was nestled deep inside its steel carbody. The power plant was the legendary General Motors 56-7B Series prime mover, a massive two-stroke V16 diesel engine that redefined heavy industrial power. The numerical designation of 56-7 was derived directly from the displacement of a single cylinder, which contained 567 cubic inches of volume. When multiplied by 16 cylinders, the sheer volumetric appetite of this engine was staggering, requiring a constant, immense rush of air to sustain combustion. Because it was a two-stroke design, it did not rely on the piston's downward intake stroke to draw in fresh air. Instead, it utilized massive gear-driven roots blowers mounted on the rear of the engine block to physically force-feed air into the cylinders. This forced induction system gave the engine an incredible power density and exceptional throttle response, allowing it to spool up and deliver torque much faster than contemporary four-stroke diesel engines. However, this two-stroke architecture came with a distinct set of operational quirks and an absolutely deafening acoustic signature that crews had to endure. The constant mechanical whining of the roots blowers, combined with the percussive detonation of 16 massive cylinders firing with every single revolution of the crankshaft, created a relentless, rhythmic chant that echoed off canyon walls and vibrated through the floorboards. The B-series iteration of the 56-7 engine introduced in the F7 solved a critical, fatal flaw that had plagued the earlier A-series engines used in the F3 locomotives. The earlier engines suffered from chronic upper-deck water leaks, where cooling water would seep past inferior seals, trickling down into the lubricating oil reservoir and systematically destroying the main crank bearings. Electromotive division engineers redesigned the cylinder head seating and cooling passages for the B-series, finally creating a prime mover that could run at its maximum rated output of 1,500 horsepower for hours on end without structurally compromising itself. Yet, for all its thunderous noise and impressive displacement, the V16 prime mover did not directly turn the wheels of the locomotive. The F7, like almost all American diesels, was fundamentally an electric locomotive that happened to carry its own immensely heavy power plant on board to generate electrical current. The crankshaft of the diesel engine was bolted directly to a massive direct current main generator, which converted the rotational mechanical energy into raw electrical power. This generator was a complex, heavy piece of copper and steel engineering, utilizing carbon brushes, dragging across a rotating commutator to transmit thousands of amps of direct current power down through thick cables to the trucks beneath the frame. This diesel-electric transmission was the secret weapon against steam, because it essentially acted as a continuously variable transmission, decoupling the speed of the diesel engine from the rotational speed of the driving wheels. A steam locomotive engineer had to balance the physical cutoff of steam valves with the speed of the pistons, struggling to maintain traction at low speeds, whereas the diesel-electric system could apply massive, smooth, continuous torque to the railhead right from a dead stop. Translating that massive electrical current into physical forward motion required a robust interface between the locomotive frame and the steel rails beneath it. This interface was provided by the iconic Blomberg B truck, a two-axle truck design that became the undisputed gold standard for North American diesel locomotives for more than half a century. Named after its lead design engineer, Martin Blomberg, this truck utilized a highly innovative suspension geometry featuring outside swing hangers. By placing the swing hangers on the outside of the truck frame, rather than hiding them between the wheels, Blomberg significantly widened the spring base of the locomotive, dramatically improving its lateral stability. When a Santa Fe passenger crew was hurtling a beautifully painted Warbonnet F7 across the poorly maintained jointed rail of the western deserts at 90 miles per hour, those outside swing hangers absorbed the violent side-to-side hunting motions that would have derailed a lesser machine. Mounted inside those Blomberg trucks were the actual muscles of the locomotive, the four D27 direct current traction motors. These motors were axle-hung and nose-suspended, meaning half of their immense weight rested solidly on the driving axle itself, while the other half was suspended by a heavy spring pack attached to the truck frame. This arrangement meant there was an enormous amount of unsprung weight crashing directly against the rail joints, which battered the track infrastructure far more aggressively than the carefully balanced driving wheels of a modern passenger steam locomotive. Each traction motor received direct current from the main generator above, using magnetic fields to turn an armature that drove a pinion gear, which in turn rotated a massive bull gear bolted directly to the 39-inch steel driving wheel. The D27 motors introduced on the F7 featured significantly upgraded electrical insulation compared to older models, allowing them to handle higher continuous electrical currents without physically melting down under the immense thermal load. But this continuous electrical transmission came with a hidden high-stakes operational cost that engineers had to actively manage to prevent catastrophic equipment failure. At very low speeds, such as when dragging a heavy freight train up a punishing 3% mountain grade, the traction motors rotated slowly, generating very little counter-electromotive force to resist the incoming current from the main generator. If the engineer left the throttle in notch 8, the maximum power setting, massive amounts of electrical current would flood the slow-turning motors, creating terrifying amounts of waste heat that could quickly overcome even the upgraded D27 insulation. If the copper windings inside the traction motor got too hot, the insulation would burn away, resulting in a violent electrical flashover, a localized explosion of vaporized copper and electrical arcing that instantly destroyed the motor and sometimes welded the driving axle solid. To prevent this, the electrical system relied on a complex process called transition, where the circuitry dynamically rewired the connections between the four traction motors from a series circuit to a parallel circuit as the locomotive accelerated. Managing this electrical transition while hauling massive tonnage over treacherous mountain passes like the Santa Fe's Cajun Pass or Raton Pass was an intensely stressful ballet for the operating crews. Early EMD F series locomotives required the engineer to manually shift a transition lever on the control stand at very specific speeds, essentially shifting gears in a massive electrical transmission while trying not to snap a drawbar or melt a motor. By the time the F7 was rolling off the assembly line, Electromotive Division had introduced automated transition systems, but engineers still had to meticulously watch their load meters, a specialized ammeter on the control stand that indicated how close the traction motors were to a thermal meltdown. The load meter had a continuous rating, a safe operating zone where the locomotive could pull indefinitely, and a short-term rating, a red zone where the engineer only had a handful of minutes to crest the mountain before the motors baked themselves to death. The battle against gravity on the slopes of Raton Pass was no longer fought by a fireman desperately shoveling coal into a white-hot firebox. It was fought by an engineer staring intently at a dial, praying the amperage would drop before the electrical insulation failed. Knowing what you now know about its massive electrical limitations and grueling operational demands, do you think this design was a mechanical triumph or an evolutionary dead end? Share your thoughts below. The true tactical advantage of the F7 on these brutal mountain grades was not just its pulling power, but its ability to multiply that power effortlessly through multiple unit control. A single F7 unit produced 1,500 horsepower, which was frankly unimpressive compared to a massive steam locomotive that could generate 4,000 cylinder horsepower at 60 miles per hour. However, the diesel-electric design allowed the railroad to mechanically and electrically link an A unit, which possessed a control cab, with several cables as B units, creating a massive, articulated chain of motive power controlled by a single engineer. The Santa Fe famously operated their F7s in an ABBA configuration, a 4-unit lash-up that placed 16 powered axles on the rails, distributing the weight and traction evenly. This 4-unit combination delivered over 200,000 pounds of starting tractive effort, allowing it to rip massive, heavy trains away from a dead stop with a sheer brute force that no single steam locomotive could ever hope to match without violently spinning its wheels. When the struggle against gravity reversed and a heavy train had to safely descend the mountain without melting the brake shoes or causing a runaway, the F7 utilized another brilliant technological innovation called dynamic braking. By manipulating the electrical circuitry, the engineer could turn the heavy traction motors in the trucks into electrical generators, using the crucial rotational kinetic energy of the rolling train to generate power. Because the locomotive had nowhere to store this newly generated electricity, it was routed up to the roof of the locomotive and dumped into massive banks of resistor grids, converting the electrical energy directly into intense heat. Large cooling fans mounted on the roof roared to life, blowing ambient air across the glowing hot resistor grids to dissipate the energy into the atmosphere. The distinct, high-pitched, jet-like whine of a 4-unit F7 lash-up descending a grade in heavy dynamic braking became the new soundtrack of the American mountains, replacing the screech of smoking, overheated cast-iron brake shoes. While the F7 was conquering the mountains, it was also fundamentally dismantling the traditional culture and layout of the railway roundhouse and maintenance shop floor. For decades, steam locomotive maintenance had been an art form heavily reliant on localized craftsmanship, requiring machinists to custom turn specific parts on lathes to account for the unique wear patterns of every single locomotive. The F7 eliminated this bespoke maintenance in favor of modular replacement, utilizing parts that were precision machined to exact tolerances at the General Motors factory and shipped in wooden crates. If a cylinder on the V16 prime mover suffered a failure, a diesel mechanic did not need to spend days custom machining a new piston and liner to match the worn engine block. Instead, they utilized a forklift and a crane to extract a standardized power assembly, a pre-assembled unit containing the cylinder head, liner, piston, and connecting rod, dropping a brand new one into place and returning the locomotive to service in a matter of hours. This modular efficiency was an absolute godsend for the corporate accountants, but it was a bitter, uncomfortable truth for the thousands of skilled steam mechanics whose hard-earned expertise was suddenly rendered obsolete. The railroads no longer needed master blacksmiths who could perfectly forge a main rod by reading the color of the hot steel. They needed electricians who could read complex wiring schematics and mechanics who knew how to operate torque wrenches. The transition from steam to diesel was incredibly brutal on the human level, resulting in massive layoffs and the rapid closure of hundreds of small railway towns that had existed solely to service thirsty, high-maintenance steam locomotives. The F7 was the primary instrument of this economic devastation, proving definitively that high initial capital costs for standardized machines were vastly superior to the endless, spiraling labor costs required to keep the old iron horses running. Inside the cab of the F7, the human experience for the operating crew was vastly different from the open, element-exposed decks of a steam locomotive, but it was by no means a luxurious or entirely comfortable environment. The crew sat high up in the iconic bulldog nose, separated from the thunderous prime mover by a steel bulkhead, which provided a cleaner environment completely free of coal dust and swirling ash. However, they were still subjected to immense amounts of noise as the mechanical racket of the V16 engine and the whine of the main generator penetrated the thin steel walls, requiring crews to shout to communicate signal indications. The cab was often brutally hot in the summer, with the immense heat from the electrical control cabinet located just behind the engineer radiating forward, while primitive pneumatic windshield wipers violently slapped back and forth during winter storms. Furthermore, sitting directly over the front draft gear and the lead truck meant the crew felt every single jolt and dip in the track structure, riding out a violent, bounding motion that could throw an unprepared fireman completely out of his seat. Despite these ergonomic shortcomings, the engineer's control stand was a masterpiece of simplistic, functional design compared to the sprawling array of specialized valves and gauges required to operate a steam boiler. The primary control was the throttle lever, an 8-notch handle that electrically communicated with the engine governor, commanding the E16 prime mover to increase its revolutions per minute and dump more fuel into the cylinders. Beside the throttle was the reverse lever, and below that was the heavy brass handle of the automatic brake valve, which controlled the pneumatic air brakes for the entire length of the train stretching out behind them. There was no steering wheel, no complex boiler water level glass to monitor, and no terrifying possibility of a low water boiler explosion that could instantly vaporize the crew. The diesel engineer was essentially a manager of electrical currents and pneumatic pressures, operating a heavy industrial power plant by wire, insulated from the fiery mechanics of combustion that defined the previous century of railroading. The dominance of the EMD F7 becomes even more apparent when compared to the machines produced by rival manufacturers during the same era, most notably the American Locomotive Company, and their beautiful PA1 passenger diesel. The Alco PA1 was arguably a more aesthetically elegant machine, featuring a massive long nose and powered by a highly advanced 4-stroke turbocharged diesel engine that produced incredible horsepower. However, Alco's prime mover, the venerable 244 engine, was rushed into production and suffered from catastrophic mechanical failures, including snapping crankshafts and notoriously fragile turbochargers that frequently caught fire under heavy load. While the Alco machines spent days in the maintenance shops having their complex turbochargers rebuilt and their engines realigned, the simpler, naturally aspirated 2-stroke F7s just kept running, day after day, logging millions of miles of revenue service. The Santa Fe owned both models, but it was the EMD F series that they fundamentally relied upon to maintain the incredibly tight, demanding schedules of their premier passenger trains and their vital priority freight movements. The sheer ubiquity of the F7 design eventually led to its own unglamorous demise, as the realities of freight railroading shifted toward the end of the 1950s and into the 1960s. The sleek, enclosed carbody design that made the Warbonnet look so brilliant on a passenger train proved to be an absolute nightmare for switching operations and local freight service. The carbody completely eliminated rearward visibility, meaning an engineer trying to reverse an F7 to couple onto a string of boxcars had to rely entirely on a switchman hanging off the rear ladder, frantically communicating via hand signals. Furthermore, if a mechanic needed to perform minor maintenance on the prime mover, they had to squeeze down a narrow, oil-slicked, incredibly noisy corridor inside the carbody, rather than simply opening exterior hood doors. Railroads quickly realized that they did not need aerodynamic streamlining for freight trains, moving at 50 miles per hour. They needed practical, utilitarian machines with external walkways and massive glass windows for all-around visibility. This realization led directly to the development of the road switcher concept, epitomized by the EMD G P7 and its successors, which essentially took the mechanical guts of an F7 and placed them under a narrow hood on an open deck. The road switchers were vastly superior for the day-to-day grit of freight railroading, allowing crews to switch cars effortlessly while providing maintenance personnel with incredibly easy access to the prime mover and electrical generator. As the road switchers took over the massive freight duties, the aging fleets of F7s were slowly relegated to secondary trains, commuter runs, and eventually the scrap lines, stripped of their glorious paint schemes and left to rust. The transition era had concluded, and the enclosed cab unit diesel, having successfully murdered the steam locomotive, was immediately rendered obsolete by a much uglier, vastly more practical evolution of its own internal technology. Yet, the legacy of the EMD F7, particularly when adorned in the stunning Santa Fe Warbonnet livery, remains permanently seared into the cultural consciousness of American industrial history. It was a brutal, uncompromising machine of corporate efficiency wrapped in the deceptive guise of aerodynamic luxury, a mechanical paradox that perfectly encapsulated the post-war transition. It proved definitively that massive, complex engineering challenges like moving thousands of tons of steel over mountain passes could be solved not by building bigger, custom-forged behemoths, but by linking together standardized, mass-produced modules. The F7 did not just replace the steam locomotive. It fundamentally rewired the entire financial, cultural, and operational structure of the railroad industry, turning an art form into an industrial science. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.